So let me start the class about introduction to the introduction of quantum computing. Only a high-level discussion, right? We know quantum computing is very, very important, seems to be. And how quantum computing is different from regular computing or classical computing, right? In my opinion, we can summarize it as that it uses the superposition and entanglement to do the computation. All our classical computer, we are already using quantum mechanics. What is a transistor? It's all quantum mechanics. With quantum mechanics, you know what's conduction band, valence band. You have a band gap. That's all quantum mechanics. Classical mechanics cannot give you this band gap, right? But the quantum computer, the main point is superposition and entanglement. They use these two special phenomena. You might not know it exactly what it is at this moment, but memorize it. And your goal in this semester is to understand them and be able to describe them, okay? I will also say interference is also very important. Now, this is again quantum mechanics. How come you can have interference with electrons or a spin, right? Or a particle, whatever, right? Because quantum mechanics have the wave-particle duality, right? But the interference I'm saying is that we are not going to so deep to look at the physical interference. What I'm trying to say that quantum computing is very rich in information. While it can do exponentially a lot of data processing and exponential speed up in some processing, you cannot get all the information inside this process. In order to get the information you want, you need to come up with a smart algorithm. And then use interference to single out the one that you want. Right? We will see that at the end of this semester also. So I want you to remember these three keywords: superposition, entanglement, and interference. Nowadays, there are two major types of quantum computing. One is the so-called gate-based, right? It means this slide, this set of slides. Another is quantum annealing. So on the right, this is the so-called gate model quantum computing. It's very similar to a classical computing, right? You have different gates, you have an input, and then eventually you do the measurement. Now, the difference is that this line actually showing the time instead of the space. We'll learn a little bit more later. So in a circuit, you put an AND gate, NOR gate, adder, subtractor, and then you get your output. You usually lay out it on the integrated circuit. But for a quantum computer, usually, for example, the Josephson junction-based quantum computer, your qubit does not move, right? So your signal does not propagate from one point to another point. The so-called gate is actually you shine some laser pulse or microwave pulse to the qubit, okay? And then they evolve. So TI1 is saying, say, I shine a pulse of NOT gates, then I shine a pulse of Hadamard gate and identity gate, then you keep evolving, okay? It's just like you're cooking something in your oven. You change it to 100 degrees C and then change it back to 50 degrees C. It stays there, you keep make it evolve. We will understand more later. But this is the gate model. It's more generalized. You can solve all the most of the difficult problem if it works. Another is something called quantum annealing. So this is very interesting. You map the difficult problem into a physical problem. You can Google for D waves, which is a pioneer in this field. And what you do is that you try to map the problem, some very difficult optimization problem, to a quantum computing circuit. And then you let it evolve and find the minimum energy. And that energy is going to be correspondence to your optimized solution. Now, quantum annealing is just like you have this energy landscape. Your initial guess may be here. The global solution may be here. And you want to do something so that the solution will go to here. But because they use this quantum annealing, you can even have tunneling through this barrier. In a classical one, you need to do something so the energy is high enough to go over the barrier. But now you can do tunneling so it can get to the global minimum much easier. Okay? This tunneling is just a simple tunneling of like electron through a barrier. It's in another space, but just think it in this way, right? So we have two types of quantum computer. And in this class, we will only talk about the gate model. Okay? We have a lot of application to quantum computing. Why they're important? Because they are fast, and nowadays we are facing a lot of challenge to design new material and new drug in the industry. If you have quantum computer, in principle, it can speed up the design or the finding of new drugs or new material exponentially, and that is very important, right? Think about develop the vaccine for COVID. If at that time we had quantum computer, maybe they just come up with vaccine within 1 day when they discover the COVID, right? Instead of they need to do a lot of trial, they can just use quantum computer to do that. Secure communication, this is related to, we are not going to talk about this, but this is related to entanglement, that in principle, you can establish a non-breakable communication through quantum communication, okay? You use it to do optimization, like what I said, what's so important about optimization. Like Ford, they want to think about the supply chain, how they supply all the parts to different city and all the costs, how should they locate the vendor to minimize the cost. This is a very difficult problem. People call it NP-hard problem. And if you can use quantum computer, you can find this very fast. And usually nowadays they use quantum annealing. Yes, question?
So this very example you just gave, like a server running the machine learning, traditional technology which we already have cannot do it better, or can it?
Yeah, they just cannot do it better using the traditional classical. Even you have GPU, they just help you to speed up, maybe linearly. But what we're looking for is exponential speed up. This type of problem is that if you have one, let's say, variable, it spends you 1 unit of time. 10 variable, it spends you maybe 2 to the power 10 unit of time. And then 3 variable, maybe 100 variable become 2 to the power 100. So they go up exponentially in terms of the computation time. So using classical one with NVIDIA or the cloud server, right? They can only increase maybe 10 times faster for all of them, and they cannot go up exponentially.
Okay.
Yeah.
Another question. So on a physical level, the different, so the gate model versus quantum annealing, but if you look at these two quantum computers on a physical level, are they using the same structures? So for instance, you can use superconducting material to build the gate model, and it seems to me you can use the superconducting material to build quantum annealers. So it seems to me on a physical level, they're the same, maybe on an operational level.
In terms of device level, they can be the same. So indeed, for D-Wave, they also use the Josephson junction. And you know, Google and IBM, they also use Josephson junction, right? So they use the same physical thing. But then, in terms of the operation, they will be different. So like D-Wave, they already have a 5,000 qubit quantum computer, but they can only do quantum annealing. Yeah. Okay, so we talk about optimization. Finance is also important. For a certain portfolio, you have so much money, and you say, I want to have 10% return. What is the best investment I should have in today's market? There are so many stock, bonds, and debts that you can buy, right? And that is very difficult to optimize. So if you look at the news from all those quantum computing companies, you will see that the financial company are their important customer already. Because whoever can get it right first, they will earn a lot of money. Okay? Again, this is optimization problem. Yes?
So there's like a confusion here. So I hear but is there like an industry consensus that we have gotten quantum supremacy in these particular applications, or is it something that, okay, there is interest, and let's say the JP Morgans and the Chase and the worlds are looking into quantum computing and they're trying to figure out, hey, what's the investment opportunity for us? And they're in that process, and there's no consensus yet that they can use quantum computers and actually come up with a better.
Okay, that's a good question, right? I hope that I can answer, right? So he talked about quantum supremacy. Now we say quantum computer is so good. You need to show me you are really better than classical computer. So nowadays it's still very difficult. Google has some paper to show that they can do some computation within a few seconds, hundreds of seconds, while classical computer need to do it for 10 billion years. But then the next year or 2 years later, a Chinese research team, they use supercomputer to solve the problem in a few days. So instead of 10 billion years, they can do it in a few days in classical computer. And that is a very specialized problem, right? But they try to show the quantum supremacy. Now, regarding your question about is there any financial company that already achieved this? I don't know. They did not announce. I think they will keep it as a secret if they really can do that, right? Because they're going to earn a lot of money. But I guess not. Because we still don't have enough qubits that can work well due to the error, right? So, but however, they already saw that for some simple question problem, they can get it much faster than classical computer. However, if they can access to a supercomputer, maybe the result is the same. The point is that if you only have this limited hardware, I think they already see in certain problem it is better in quantum computing. That's all I can say.
But those are simple.
Simple.
No matter
Right. I never seen this case. But again, my knowledge is limited. But I don't think this case is there, that they already see the supremacy. Right? Yeah. But that is the hope. Okay? That's why you are here. Okay? So let's talk about the basics of quantum computing. Right? The state. How do you represent information? Well, you all know that we represent classically with 0 and 1, right? And then we have the binary digit. Physically, how do you do that? You can use a coin, head and tail, no problem. You can also say happy and sad. Actually, you can do that. Why not? But they are just not robust. We decided to use the transistor on and off, right? You know very well, and we can put in an integrated circuit, right? This is called a state. I want you to memorize this word, state. Every physical system can be described by a state. It becomes so simple. No equation, just write it down. It's a state. My state is happy, my state is sad. I'm a complex physical system, right? So information represented by state. How about for quantum computing? Same. We have something called basic state. The basic one. What does it mean? Well, I'm going to write the 0 and 1 in a bracket. Right? Just take it for granted. That's why we want you to get in this class. This is called direct bracket. Learn it, get it. It's nothing special, just a bracket to 0 and 1. If you teach the left to a kindergartner first or teach the right to a kindergartner first, it's the same for that kindergartner. They don't understand what you're talking about, 0 and 1 or 0 with this bracket. It's the same, right? So again, I can represent this basic state with a coin, head and tail, but it's a basic state, okay? Sad or happy, or even transistor on and off, right? They all represent a state, the basic state, no difference between classical and quantum computer. Is this okay? So if you are only allowed to work on basic state, quantum computer is the same as classical computer. So it's not special quantum computer. It just includes a classical domain. But what makes quantum computer so special is that you can have so-called superposition. Now, why? You take it for granted. People argue it for 100 years. I think 100 years, yeah. It was invented in 1921, right, by Schrödinger. 1920s, by Schrödinger about quantum computing. Superposition, right? Take it for granted in this class. We won't discuss this philosophically. So for a state, besides the basic state, remember I said basic state, It can be a linear superposition of the basis state. Okay, so I can tell you, I have a coin spinning on the table. Is it head or tail? You don't know. I can say it's a linear superposition of head and tail. Now, this is not quantum computing. This is just analogy, right? So do not take this, say I'm going to make a quantum computer using a few coins. I just keep spinning it. I have a quantum computer. No, this is just an analogy. But I want you to understand that the spinning coin is a state, right? A physical system. You can say it's a linear superposition of head and tail. This is what I want you to know, and that is why it's powerful, because it can process information through superposition. Now, if that is the case, we'll talk about quantum register. On the left is the classical register. I think you all learned about this in digital circuit, right? I have 4 bits. I can represent it as 0, 0, 0, 0. It represents 0. 0, 0, 0, 1, it is 1. 0, 0, 1, 0, it is 2 in decimal. 1, 1, 1, 1, it is 4. It is 15 in decimal. Is this okay? Everyone happy with this? So I have 4 bits. I can represent 16 values. And that is what your computer is doing. What if I have 4 qubits, right? I say qubit. I even did not introduce qubit yet. Just a quantum bit, okay? Someone make it for you. The physics people, they did that. Physicists, they did that. You take it for granted. I have a qubit. Now, I can use it to represent the basis states also. So I can have 0, 0, 0 basis state. Then it represents a 0 if I say it is in decimal. I can also have 0, 0, 1. Then I have 1 in decimal. How about 0, 0, 1, 0? Then I have 2. 1, 1, 1, 1, I have 15. What I'm talking about? What is the meaning of the 1 here? You just think that that qubit is at the basis state. Is this okay? Because I already told you the qubits can be in superposition also or in the basis state, right? So if 1 is 1, then you put 1 here. If you have 4 qubits, then have 1, 1, 1, 1. And this is the basis state of the quantum qubit. I guess you will, yeah. Exactly. And direct, you also don't need direct notation for the superposition. But I want to introduce you now. I don't want to go through another lecture just to say what is direct. But now this is an overview, right? If you don't understand exactly, that is fine. Okay? But I want to start introduce with something, and in this class I keep repeating important concept so that you get brainwashed by me. Actually, that is my purpose. You feel that it's so natural to have this thing. Okay? Now, but what I'm trying to tell you here is that if I have 4 classical bits, I can represent 16 values. If I have a 4 qubit, I can represent 16 basis state. No difference. The difference is that I can also have a state that is a superposition of this basis state. Now, think about you have 4 transistors in the classical sense. It's either 0, 0, 0, 0, 0, 0, 0, 1. You cannot say that it has half chance 0, 0, 0, 0 and half chance of 0, 0, 0, 1, right? If that happens, that means your computer is not working. You need to be at one of the states. But if you have 4 qubits, besides that you can have this 16 possible states, it can be a linear superposition of this 16 states. Now look at this. When I talk about 2 qubits, you have, 1 qubit, you have 2 basis states, right? 2 to the power 1. 4 qubits, I have 16 states, basis state, 2 to the power 4. If I have n qubits, I have 2 to the power n basis state. So basically what I'm saying that if you give me n qubits, I just put it there. And then it can contain a lot of information because the state of this n qubit, just as a system, like me, myself is a system, is a superposition of 2 to the power n state. Start from, these are the coefficient, A0 of this, of 0, A1 of 1, up to A2 to the power n minus 1 of 2 to the power n minus 1. Okay? Can be confusing, no problem. We're going to do this in the following lecture. But what is the power of this? What if I have 300 electrons? 300 electrons is really simple. We have 2 billion transistors in an Intel chip, right? 300 electrons means 300 qubits. How many states do we have? 2 to the power 300. Because 1 qubit is 2 to the power 1. 2 qubit, you have 2 to the power 2. 3, 2 to the power 3. 300 qubit, you have 2 to the power 300 basis states. It means I have 300 0 here and 300 1 here. You count it, you won't have time to count. Before I finish counting, I die already because it takes really long time to count, right? So 2 to the power 300 state means 10 to the power 90 complex number because each state has a complex number associated to it, right? Each basis state, just like here. Each basis state have alpha and beta, right? This is 0 and 1. Here, same, right? How do you describe this system? 2 to the power 300 complex number. You think that maybe, yeah, I just buy more SSD. It doesn't work. The number of atoms in this universe is less than 10 to the power 82. The number of bytes of state of storage in the world at this moment is less than 10 to the power 21. It means even you are very rich, you buy all the SSD in this world, you still cannot store the states of 300 electrons that combine together. Assume that you know what the state is. Assume that you know what is A0 to the power A to the power 300 minus 1. So there are tremendous of information in quantum computing because it stores a lot of information. That is the first thing, right? You just cannot use the classical computer to simulate this. That is first thing. But all the things like like all chemistry or whatever, they are quantum system. How do you describe that? You need to actually use quantum computer to solve it. Is that clear?
So I guess one constraint, if you sum all these A's from 0 to 1, they should all add up to 1.
You sum up the square of the magnitude of them, they should add up to 1. Very good. That I will discuss very soon. He's talking about what is the meaning of A0 to A to the power 2n minus 1. Yeah, you're right. Let's talk about quantum parallelism. Now, I say it stores a lot of information. That is cool. Maybe we can use it, right? Just one state. 300 electrons store a lot of information that you cannot store in all the memory in the world. Another is quantum parallelism. If I assume this state, right? Quantum mechanics is linear. I try to apply a function to operate on this state. Then I can distribute my function to them. So I just use one operation. I can perform the computation of F0, F1 all the way to F3 in one shot. Well, you have 300 electrons. I perform 2 to the power 300 computation in one shot. That is the quantum parallelism. Okay? Sometimes people will talk about the superposition as so-called multi-world interpretation. Right? That is very philosophical. Right? They're just saying that maybe they're multi-universe. Each of these universe has a wave function. But we don't discuss philosophy here. The simple picture is that you can do all the computation in one shot. Whether you think that they're multi-universe, each of the universe do the computation for you at the same time or whatever, okay? You get this speed up, right? A lot of information and then speed up. So I hope that you start appreciate why quantum computing is important, right? Later we will really go to the real algorithm and you will appreciate why it has the speed up. Okay?
Can I
Yeah.
just come back? Many very, very interesting, but I guess is one way to read this that you're trying to do this operation, this function, and you already have four possible answers, all those four answers are available to you at once. And by the single shot operation, as you called it, is what's choosing between one of those four realities.
No, but when I say single shot, it's like you apply to the real state, and then it will compute all this at the same time, right? Because it's linear. However, you don't know what is the individual value. So I think you may already see the problem. Yes, I can do four computations at the same time. How do I get the value? What I'm doing is just apply to this state of the 2 qubit. This is 2 qubit because it's 4 basis states. I just apply the operation to 2 qubit, and then it evolves to something. But in this evolution, it is equivalent to applying the operation to this 4 basis state, just based on this equation, because it's linear. And they do it in one shot. Let's say this take 1 millisecond, then I get all this answer in 1 millisecond. If I have 300 qubit, I get 2 to the power 300 operation in 1 millisecond. Okay? But now you are start seeing the problem. How do I know the answer? That is the problem. We'll discuss later. Okay? So now is the information is there, but you cannot get it yet. Okay?
You choose 0.5.
Very good. Maybe this slide will explain to you why I choose 0.5. How do we do measurement?
Flip a coin and see where it lands.
Yeah, stop the coin. When you stop the coin, what will happen? Either head or either tail. Same, if I have a superposition state, I try to do a measurement, it will give me the basis state, one of the basis states when you do measurement. Okay? That's why people say if you don't look at the moon is not there. The moon is there because when you look at it, the wave function collapses, because if moon is a quantum object, it is everywhere in the world, even it's at your home, except that it has super low probability to be at your home, right? But it is not quantum object because it's macroscopic. But the point is that we will collapse randomly. Like you stop a coin to either head or tail. But the probability is going to collapse to what? 0 is proportional to the square of the magnitude of the coefficient in front of it. So what is the probability to collapse to either 0 or 1? It must be 1, right? So that's why we say all these coefficients square, they're complex numbers, so you need to take the magnitude square, must add up to 1. Now go back to your question. How I chose 0.5? Because I was lazy. I only know that 0.5 squared times 4 is going to give me 1. 0.5 squared plus 0.5 squared plus 0.5 squared plus 0.5 squared. I can use other number, but I just choose this particular state. Correct. You need to make sure they all sum, they are square or sum to 1, because they represent the probability of measuring this state. And you must have a 1 when you sum them up. Sorry, you go first. You cannot, because this is just quantum mechanics. They have to sum up to 1. And later we will learn about normalization. After you do the measurement for multiple qubits, then you need to renormalize your wave function so that their length is 1. This, later you will learn that these are just vector. So it basically means that all the states are unit vector. You cannot have a non-unit vector. Otherwise, it will violate the physics. Okay.
Yeah, just
No, not probability and complex number. It can become because you take the magnitude. So you don't really square the probability. You take the magnitude of the complex number and then square it. So it is a real number for probability.
so
There is just the coefficient, you're right. And it's square, like what I'm putting here, right? The magnitude square, alpha, is the probability. Make sense? I hope you understand what he asked, because he's asking something very important. You do not make this mistake later, right? Do not give me something probability is complex or whatever. It's the magnitude square. Is that okay?
Is there another?
I just call it coefficient. Yeah. Okay, because of the time, maybe I will stop here and then continue on Wednesday.